Yep. All right, so I don't have my Apple Pen with me, so you have to use my finger. So anything I draw on here is going to be even worse than normal, unfortunately. But yeah, this is chapter 5. All right. So one thing that's important to know, and this is really wordy, but the crux of the matter is whenever molecules come together, whenever atoms come together to form a molecule, the overall molecule can have very different properties in the single atoms. Like water behaves very differently than either hydrogen or oxygen. Both of those are gases at normal standard temperature and conditions, and they're both highly explosive. But yet we drink water all the time. You know, we have to have water. Water is a liquid. That's because once they came together to form that molecule, they took on completely different properties. And that's what this is showing here. This is table sugar, which is sucrose, and it's C11H22O11, I believe. But that's not the important thing, is that it's just very different. Carbon by itself makes up graphite, lead, or diamond, like a diamond. It's just true carbon. That's completely different than sugar. Whereas I already mentioned the fact that hydrogen and oxygen are both explosive. Or, like literally, sugars called, what class of compounds are sugars? Or are they also commonly called? Like, you know, they're bad for you. The Atkins diet is like, don't eat them. Carbohydrates. We call it carbohydrates because the reason why is it's hydrated carbons. And so it looks very different than water, is what they're trying to show here. So, but when water and carbon come together, they can form these carbohydrates. But it's completely different than. Okay. Likewise, sodium element is explosive. Like it reacts vehemently with air. You have to keep it in oil. Okay, chloride, like the chlorine as a gas, as an element, and it's highly toxic. It will kill you. Like you split. Okay, so therefore, both of these would be really, really bad. But of course, whenever they come together, the chloride takes the electron from the sodium. So no longer are they elements or ions. And of course, it's this table salt, sodium chloride. Once again, take it in moderation. Western diet is really high in salt. So
what does it mean when it says like iodized salt?
Iodized salt means that they've added iodide anion to it, because it's not naturally in salt.
Okay.
And what you hopefully will find out in some nursing or biology or anatomy classes, you have to have small amounts of iodine, just very small amounts, and it's hard to get in your diet. And so a lot of Western diet, you put it in salt since people put so much salt in there, and so that's what iodized salt is. It's just one way that you can get iodine. Yep, they just added it in. It's actually not 100% salt, sodium chloride salt anymore. They've added in sodium iodide, usually it's sodium iodide or something, in small amounts. Okay, you need it for your thyroid. All right, and so that's why whenever they say elemental, whatever, that means it's still truly the element atom. It hasn't lost electrons or gained electrons, or it hasn't formed a bond yet. All right, and that's just sodium chloride. You know what chloride looks like? Okay. Some things you'll encounter throughout life really are still in their true elemental form. Like you can find elemental, iron or something like that out there. Elemental copper. Right? However, many times things are a mixture of these elements to form these compounds. And whenever they form a compound, it's got to be in a fixed ratio. So that's what they mean by definite proportions. For it to be water, it must be H2O. If it's H2O2, does anyone know what that is? It's hydrogen peroxide, which your body does have small amounts of hydrogen peroxide naturally in it, but you don't want to have too much. It's an oxidizer, it's bad for you as well. Okay. If it's just HO with an extra electron, it's called the hydroxyl radical, that's really bad for you. So that's why it's going to be in these very specific proportions. We'll talk a little bit about it. One of the examples that they like to use are carbon and oxygen. So we'll talk about what the differences are in just a moment. Okay. And we always use whole numbers. Like you won't have H1/2 O1. It's always H2O. We always use whole numbers. Again, this is just showing you the mixtures and coming together. Okay. Okay, it's called the law of constant composition. I will never ask you that. So like, what is it? It just means it's got to be the same proportion throughout, or otherwise it's no longer the same. Like as I mentioned, H2O, it'd have to be the same all throughout. Because if it was in some places H2O2, it's not water. Now it's hydrogen peroxide. Okay. So, all right. There is a way to do something called mass ratio. And it's literally where you take the mass of one element and you divide it by the mass of the other. And so since for H2O, you look on the periodic table, each hydrogen is around 1 gram, okay, according to its atomic mass. And one oxygen is 16 grams, and so since we have 2 hydrogens, it's going to be 16 divided by 2, and 8 to 1. Okay. At this point, one example, what is ammonia? So just to show an example that, oh, I was about to write on the iPad with a marker. Whereas if we have one difference, that's nitrous oxide. I'm sorry, nitric oxide, not nitrous oxide, nitric oxide, and this is nitrate, which technically nitrate is negatively charged. That's just, I wouldn't expect you to know that at this point. But I was just showing you this, that they have different compositions. On the first one, nitric oxide, there really is 1 nitrogen for every oxygen. And nitrate, it's 1 nitrogen for every 3 oxygens. So we could even do the mass ratio. I'm just going to do it for, well, I'll do it for the bottom one because it would be more difficult of the two. If you looked on the periodic table, a nitrogen is equal to, the mass of a nitrogen on the periodic table is 14.01. Whereas the mass for each oxygen is 16. So we'd have to have 3 times 16 on the bottom. Okay, which is 48. And you would get a mass ratio here. Oh, don't do that too much. Calculator. 14 divided by 48. Of roughly 29%. So it would be, the mass ratio here is 0.29, which if you did it as a percent, you just multiply it by 100 and be 29% nitrogen. All right. This is showing what it is for ammonia. This is ammonia, where they did nitrogen to hydrogen. All right. So these are called chemical formulas, which we've been doing. H2O is the chemical formula for water. Shows that's a 2-to-1 ratio. Ammonia, which actually I just skipped over. Ammonia's chemical formula is NH3. So there's 1 nitrogen with 3 hydrogens. Please note, and it's kind of, obviously, if you just always think of H2O, it makes it simple to realize then that you don't put the number 1, okay? There's 1 oxygen. You don't say H2O1. It's implied. So if you don't put the subscript down, it means that there's only 1 of them. Sodium chloride is NaCl. Okay. So that's just showing you. You always use the chemical symbols. Once again, make sure that the first letter is always, if it's got more than 1 letter, for example, beryllium, which is Be, you'd always capitalize the B, but you make the E a lowercase. That way you always know the capital letter indicates it's a new element every time. That's why it's capital H and capital O. Okay, just holler if you have any questions. So this is actually what we've been doing so far. Once again, sodium chloride's a 1-to-1 ratio. Carbon dioxide is a 1-to-2 ratio. And we'll explain the reason why that one says dioxide later on. I don't know that we'll get to it today, but later in this chapter. But di indicates it's a prefix for 2. Okay. Sugar is C12, H22O. Wait, that's not right. No, it is right. Yeah. Okay, because it's H2O. No, I don't think that's right. That's not right. It should be 11. C11, H22O11. I didn't type this. Okay. Because it's 1 carbon for every 2 waters, and so that's why that can't be right. And so it's got to be C11, H22O11, or C12, H24O12. I don't have it memorized off my head, but once again, if I gave this to you, this is not table sugar. This would be something else. It's 1 dehydrated. It would be a sugar substitute. Okay. And then C12, H20.
C12, H22O11. The sucrose.
For sucrose?
Table sugar.
Oh. And that's not a true carbohydrate then.
C12, H22O11.
And so, yeah, it's not a truly hydrated carbon then. Good figure. Because it's not a true 2-to-1 form for carbohydrate. Alright. But what you'll find that, oh actually no, they don't take oxidation. So you'll find out with carbohydrates, a lot of things are called carbohydrates, but they're actually not historical carbohydrates. It's just that they call everything that. It's like calling all shoes Nikes. Because it's not, if it's C22H22O11, then it's literally 1 H2O off from being a full carbohydrate. Alright, but the important thing here is that you can always tell based their formulas. You can always tell the ratio here. So this is carbon monoxide versus carbon dioxide. Okay, mon means 1, mono, and then di would mean 2. There isn't a CO3. Okay. And in this class, we never get to reasons why there's not a CO3, but it's not possible to have CO3. And have it alone, I should say. But let me just specify that. So, and have it alone, like that. Okay. However, if we didn't include that, we just said CO, and we really meant carbon dioxide, we literally can have a different compound. So that's why you have to be very specific. It doesn't matter what the subscript is. Okay. Whenever you're doing what we're going to find out is an ionic bond. The one thing I don't like about this book, and it's true with almost all chemistry books, is this chapter, regardless of wherever it is, they just tell you to memorize a few things at the beginning, and then they don't tell you to explain why until later on. But whenever we have an ionic bond, which is made between a metal and a non-metal, whenever we write out the chemical formula or we say it, you always put the metal first. So I just always think about sodium chloride. You know, you're used to hearing about sodium chloride, table salt. It's NaCl. So just use that always as the example if you need to. Whenever you need to write out an ionic formula. So if it was something like with potassium, which is K and O, you know that the K has to come first because the K, potassium, is a metal. It's on the left-hand side of the periodic table. The O is on the right-hand side of the periodic table. And technically, well, you'll find out later in this chapter, it'd be K2O. Now, any time that the compound only has nonmetals in it, you want to put the metal that's the most, you want to put the element that's the most metal-like first. Usually that's whichever of the 2 or 3 that's on the furthest left on the periodic table. So that's why they're showing, like, if you have in nitrogen and oxygen coming together, we put the nitrogen first, because it's further left on the periodic table. Okay, so that's why that would be nitrogen dioxide, that is or nitric oxide. Technically, it's actually monoxide, but it's really called nitric oxide. And same thing with sulfur. If it's within the same column, it's whichever one is lower on the periodic table. That's why sulfur would come before oxygen. Which, if you remember, let me do it this way. The periodic table kind of looks like this. Remember, there's the stair step over here, which I did not draw this to scale, but you get the idea. And so it makes sense that whatever is further down is going to be more metal-like, since there are more metals than non-metals. Or whichever one is further to the left is going to be more metal-like. Okay. Now, there are a few exceptions, just like almost anything. So one of the biggest exceptions is hydroxide. Okay. Is oxygen and hydrogen together makes sodium hydroxide, for example, or magnesium hydroxide. And then they write the O first. And so it's just a historic artifact. If you had written it, and that's whenever they're writing it out in a formula, if you'd written it backwards, typically, I probably wouldn't take it off. Now, if standardized test, I probably would. Okay, just because it would show it as being something different. Okay. All right. Now, there are a few ions where you get groups of elements that come together and they behave as one. Okay? Hydroxide is an example of that. That OH, whenever it goes to form ionic bonds with something else, it behaves together as one. So the oxygen and the hydrogen within that is sharing the electrons, but whatever it's going to bind with, for example, let's say sodium, for sodium hydroxide, it's going to take that electron away. So what I'm saying here is this. So the oxygen, I'm going to draw it this way. There's the oxygen, it's sharing the electrons with its hydrogen. However, whenever it wants to make sodium hydroxide, it literally takes the extra electron from that sodium to come over here. So it behaves as one unit. You get that second electron. That extra electron. And this would be positive. And so they give this ion here a special name. It's called polyatomic ion, which probably just means more than one. And so a lot of the polyatomic ions have oxygen in it. Nitrogen can also be in some of them, sulfur. Pardon?
Oh. Yeah, nothing. I was going to say polyatomic, which is kind of ironic because it's one compound. And I think poly is more.
Yes. No, it literally means multiple atoms within one ion. So there are multiple atoms here that are behaving as one unit. Okay. So this one's nitrate. They're showing. Here, let me make it a little bit smaller so that way it doesn't get cut off. All right, so this is the chemical formula for it. It will let you know, if you notice here, there are parentheses. And just like in algebra, you do everything with the parentheses first. So there's only one magnesium, but there's one nitrogen here, but we multiply it by 2. Because there's a 2 outside the parentheses. Just like there's 3 oxygens here, but we multiply it by 2. So that means overall, there's going to be 6 oxygens, 2 nitrogens, and a magnesium. However, they never, ever, ever write it as MgN2O6. And that's because this one's an ionic. Okay, so you never do that. That would be bad. Oh yeah, good, it's going to let me into the race. Okay. So instead, what happens is this nitrogen and these 3 oxygens act as a single unit. So that's a polyatomic ion. And it takes 2 of those polyatomic ions to form an ionic bond with that magnesium. Okay.
So it all explains the reason where they get the subscripts for these later, because I'm just going in the order that the book has it. Okay. And I don't know if I actually. Oh, the name, just so that way you get used to it, because by the end of the semester, by the end of this chapter, you're supposed to start naming them. And let me put the name down here. But yeah.
So are you going to want us for the test to memorize things like that NO3 is nitrate or OH negative is hydroxide or any of those?
There's just a handful that you have to memorize.
Okay.
Yeah, and unfortunately, that's it. There's just a handful that you have to memorize, like nitrate and hydroxide. I usually have you only do the ones that are really common.
Okay.
Mm-hmm.
Will you tell us which ones?
Yeah.
Okay.
Mm-hmm.
Yeah.
Okay, so like to name this compound, which first of all I'm using the wrong hand. Magnesium. Whoops. It's hard to write with just, my fingers are huge. Magnesium is the first word, and then that's nitrate. I just realized I didn't tell you on there. There are two types of chemical formulas that are written out. Okay, the first type, let's just look at this. Let's just pull this up. Ooh.
There's an empirical formula and a molecular formula. So far, we've been always talking about the molecular formula. I think the molecular formula is the easier one of the two to understand. The molecular formula tells you the actual composition of the compound. So, for example, with that magnesium nitrate, that was the MgO3 okay? We'll get, or like hydrogen peroxide, we'll get to this in just a moment. Hydrogen peroxide really is H2O2. Water is H2O. Sodium chloride is NaCl. The molecular formula is what we've been doing. It's the actual number of elements of those atoms in each compound.
The empirical formula
Gives you the ratio, the relative numbers. For many compounds, it's the same thing. For water, H2O is both the molecular formula and the empirical formula because it's one oxygen to two hydrogens. The easiest way to look at it is this way.
is if we take H2O2, that's its molecular formula, but see how they both are divisible by 2? So that means the empirical formula is HO.
You only use the empirical formula for a handful of things. Okay. So for this class, you use the empirical formula when you do ionic interactions like sodium chloride. They never say Na2Cl2. It's always NaCl. So for ions, ionic formulas, it's empirical formula. Okay. And I don't remember seeing it, but in doing a determination of an unknown formula, like an unknown compound, they usually can only find the empirical formula. Otherwise, I don't know that any reason why you guys can use empirical formula. Okay.
Like I said, many times empirical formula, especially for smaller compounds, empirical formula and molecular formula are the same thing. Almost always we're talking about molecular formula. Okay, let me move this all up. Let's move that off. So that's what this is showing.
So a molecular formula always has to be a whole number multiple. Now that multiple may be 1. It's like H2O multiplied by 1 is still going to be H2O. Then, I don't know why I put down here. It makes it sound like it's another chemical formula, chemical bond, but it's not. Structural formula means that they draw it out.
And we haven't even seen examples of that.
Well, actually, no, I think that I think we saw one example so far.
No, I mean, it'll make sense when you see it.
I'll show you one in just a moment. I'm not going to ask you to draw out, like in color in red and black. You know they're color coded? Obviously.
Okay, so usually,
This is the molecular. They can do it with like ball and stick
the little ball, like it looks like little balls and sticks. They can do what's called space filling model, which is the one that I showed you earlier of carbon monoxide and carbon dioxide as a space filling model. They're almost always color coded, which I have problems with some of my colors, but carbon's always gold. Always black. Oxygen's typically red. Nitrogen is usually a blue. And sulfur is yellow. But once again, and you've probably seen the models like in different places where people can build them and things like that. That's what they're telling you. Or there are ways, and I would never ask you at this point in time to draw this, but like in organic chemistry, you may have even seen people in organic chemistry or seen where they draw like compounds like this and stuff like that. That's just another way. And at this point, you don't have to know that. Just know that that's another way of drawing a chemical formula. Okay. All right. So this is just to show you the different ways that you can see the same formula for CH4. Which is methane, by the way. You do not need to know the name for methane, but it's just methane gas. So the first one is the molecular formula, which is also its empirical formula. That's the structural one where they just drew it out with lines. And then ball and stick in the space filling. It's all showing the same thing. And once you don't memorize all the colors, I will give you a color key or color code, but chances are it's too expensive to make a color exam for everybody, so. Okay. Though, one thing I do want to point out, which becomes important maybe to by the end of the semester, hopefully, is the nice thing about this kind here is it does show you three-dimensional, like how it looks, whereas this doesn't. This definitely doesn't. This one, the way they have it on, doesn't do that. Because this looks like a tripod, a camera tripod. It's called a tetrahedral shape, but whenever they go out here, it looks like it's 90 degrees, so it's really not. It's 109.5.
Are we going to know all the structures? Like the tetrahedral or 100 and whatever degree?
No, you're not. Yep, not right now. You just need to know exactly what we have to do. Yep.
So, for like the next class, are we going to do, or like I always do, but are we going to do like a review, or is there a review that we can do, like what we can expect to have on the test?
It just depends on how much we get through this week. So, like, we get through enough of this week to where maybe we'll have some time left on Friday. Otherwise, you can also, there's supposed to be someone for science in this class for at ACE as well. I don't know who that person is. And I also do have my office hours available if you go into the calendar link to sign up for. I just always ask that you do at least a day in advance so that way I know to be there. You'll be able to see if you click on it what ones have already been taken, which one I think it says available specifically. Okay. All right. These are just some terms that they use, or that we use. Macroscopic means big, macro literally means big, literally what you can see with your naked eye, whereas microscopic would be something that you'd have to have, that you can't, right? It's small. Once again, this is just for, you don't need to, I wouldn't give you this and say, okay, what is this compound? No. Without literally giving you a key that says red equals oxygen and what is that, white equals hydrogen, and you just count 1, 2, 3. But I don't do that. And one of the reasons why I also don't do that is I kept on seeing that because I have a color challenge, so therefore it doesn't make sense if I can't see it, why would I ask you to see it? It's just to let you know that it exists. So some books and stuff would have it drawn out there that way for you. All right. If you think way back things like early on, it's either chapter 1 or beginning part of chapter 2, we talk about things how they were homogeneous versus heterogeneous. Then you have a pure substance, and the fact that the pure substance could be an element or could be a compound.
And where it's tricky is there's only a handful of elements that can form compounds with themselves. Otherwise, I mean, there's only six, 7 diatomic ones, and then not through the noble gases, because remember, noble gases are just happy by themselves. So that's why you do not see something like this typically. Like you would never see if you saw this O2. Think something's wrong. Remember, this is a noble gas. It's happy by itself. It's only if you got way down to that xenon and radon that they'll start to try, that they're so big and fat that they start to be wobbly enough to be able to form bonds. It's helium is just by itself. Like helium gas is He, that's it. But there are 1, 2, 3, 4, 5, 6, 7 elements that can form bonds with themselves. I do not make you memorize them, but you probably already know one of them. O2. What is O2? It's oxygen. Especially in healthcare industry, you give someone oxygen, you give them O2. Okay. And it's because oxygen, whenever it's by itself in the universe, it likes to form a bond with itself to make O2. Oxygen, nitrogen is another one. In fact, the main component of air is nitrogen is N2, but oxygen. So that's what they mean when some elements can be molecular by themselves. So they're called diatomic elements because they like to form 2 together. Nitrogen's another one. Hydrogen gas, which is explosive. And then only the halogens. Remember that was the name that I told you, fluorine, chlorine, bromine, and iodine. I can do it as well. And that's it. But once again, I'm not going to ask you to memorize. The only exception that in nursing, you'll probably come across O2, I'm sure, when you give someone oxygen. Once in a while, they may have you do something with a prep that has to be, if it reacts with oxygen, a lot of times what they'll do is they put it in nitrogen. Okay. Or argon, which is a gas, which is a noble gas. Okay. Just that way it can't react with the oxygen. But those two are the ones in nursing. They definitely would not have hydrogen around typically, since that could be. All right, so I'm going to go ahead and